career paths. Before, I was more on the design side, working with code, developing early stage design mostly, and also tools for the company, as well as looking at digital manufacturing, like robotic assisted workflows and AI and so on. Whereas Max, on the other end of the world, in Australia, instead he had a more he had a career, let's say, closer to the construction sites, more geared with manufacturers, engineers, and so on. And of course, and I also teach at the UCL, where I run research clusters there with another partner of mine, where we try to explore some of the topics I'm going to show you today, more on an academic level. Already mentioned, like, this is the kind of work I've been doing for quite a few years in the office, like working more, again, on digital prototyping at various scales, as well as design work, computational design work in the practice. And this instead is the rather other side of ENCODE, which is, again, more dealing with construction sites and fabrication. What we like to do is then, the idea is to bring together these two experiences in something which makes both these all 5 elements together. So trying to bring a bit of design, understanding, and construction technology into the world of construction itself and products. We like to say that we develop something which we believe is a product, rather in a digital form or in a physical one. Very briefly, to summarize with acronyms, what we like to do is designing through virtual design and construction methods, as well as combining it with the PLM approach, which is a little bit less maybe popular on the AC space, but rather the standard in the product design and automotive as well. So we take care of upgrading, let's say, design, architectural design stages all the way to manufacturing and installation. I always like to say we work agnostically, and this is also why the reason why we fell in love with Speckle a long time back, in the sense that we work with 3D geometry and data. And this is really beyond any specific vendor or siloed APIs or softwares. We are fundamentally Rhino and Grasshopper heavy users, but over time we develop our own tool chains and also talk, let's say, directly with most of the AEC platforms and softwares available in the market. I'm going to show you a few projects which I think they give a bit of an overview of our interest, as well as show the adoption of Speckle over time, like in a kind of gradient, starting three years ago with the very first instance, let's say. So the very first one is this project. Actually, they're all built projects except for one, which is to be built. Is getting into CNC milling. Is going to start in a couple of weeks' time, so it's also exciting. This is the first project which we have been involved for a good 6 months, 7 months. It is a large grid shell located in the heart of Sydney. It's all mass timber, glue laminated timber. It's like 50-meter span, 25-meter cantilever. We work together with a great team made by Theka Timber, which was the timber supplier and steel supplier, and TTW as an engineering, general engineering, and Kane Construction as a general contractor. So we were appointed in this project very early on in what we like, let's say, the project stage we like the most. Well, actually, I'm going to talk about that later. In general, as a methods of production, let's say, of general approach that we have is this development of highly accurate 3D models. We like to call them zero tolerance models, because they are fundamentally digital replica of the final physical artifact. So they include not only design, it's not only about design coordination, but it's really embedding every single detail into the 3D space, including tolerances from installation requirements, engineering requirements, manufacturing requirements, and so on and so forth. And the 3D assets for us is really like a central repository of informations, which before Speckle has always been very localized in our own machine. So nowadays, thanks to Speckle, we can also communicate or make these data-rich models available to anyone in the team. I said central repository because the 3D assets become, again, the only source of truth from which we generate all a series of documentations spanning from typical drawing, 2D documentation in drawings, dashboards, data charts, assembly information, as well as machine code or machine files. These models are constructed through this kind of methods, which I like to call digital continuity, which is based on chaining together different levels of representation from fundamentally graphs, data structures, which contains mostly topological informations, all the way to machine code into one single file. So everything is chained together. So at any moment in time, if something changes, even during installation, we can reissue a full set of informations all the way to communicate straight with the manufacturer. So as I said before, in this project in particular, we jumped on board very early on, before tender, which is usually the kind of stage we prefer to be involved with. Because we as a first, let's say, iteration, we could analyze the model, the general design, which was a kind of early SD stage in UK terminology. And we could anticipate some of the complexity which would have become very challenging later on in the process, and eventually also very costly. So talking early on with suppliers and manufacturers, the guys on the shop floor, we could identify through analysis some of these connections, which were one of the most challenging elements of the project, criticalities that could be then assessed early on, and then again to develop a strategy to then lead to manufacturing in a smoother way. So as you see, everything is 3D modeled to the screw. Everything is captured in 3 dimensions. And all these elements are data rich, so they contains information about, of course, their positioning in space, but as well as their relationships which maintain with all the elements that are connected with each other. Drawings, as much as we don't really like them, they're still quite part of it. So we tend to automate production of both parts drawings as well as assembly drawings, again, straight from Rhino. So we can issue big packages of 400, 500, 600 drawings. In this case, was over 600 drawings in a relatively short time, and also de-risking the entire process of QA, which is, of course, in place in various forms. Transportation. This project was, I didn't mention that, was fully manufactured in Europe and then shipped over to Australia. So it had a huge constraint in terms of transportation, mostly to contain costs. We helped out the team, again, early on, before tender, to estimate the minimum number of containers that could be used. We developed our own 3D spatial binning algorithms, which would pack all the elements into container sizes, standard container sizes, that then to price fundamentally the bid more accurately. And eventually the project continued, so we managed to develop the whole projects all the way till installation. As you can see, Speckle was, even though this is you might recognize the newest UI, but it has been just refilmed. It was was still a few versions ago. But the 3D model with all the data was shared through Speckle to the rest of the team, and became really important, especially during installation. So the installation company could actually query the model itself and color objects by properties, like nothing really out of the box. Everything is actually out of the box on the Speckle side, but has been really, really helpful in communicating with the various people in the project. As I said, like we are also developing things depending on the project needs. We like to take things from first principles and develop ground up from foundational, again, code, foundational research papers. In this case, for example, we were asked to deliver like fully working CNC files. So we started to develop our own framework for that, which could run straight into Rhino, and allowed us eventually to, again, streamline this process of 3D modeling to manufacturing right away within the Rhino ecosystem. And this, over time, of course, it's been consolidated. It's been compiled into plugins, which are now more easy to consume, like, and can be accessed to also less code-savvy people. And very last, like we were appointed also to, in a late stage, to assist the installation phase. And particularly interesting was this kind of daily scanning of the structure while it was built up. And we were running in parallel analysis to compare what was digitally planned against what was physically built. So every day they had like pretty much like a digital assist to proceed with installation, compensating tolerances. This was also brought into Speckle, so we could analyze deviations and then give them access to the 3D model with all the measuring points and the deviation on in specific locations of the structure. This was the construction site. Maybe I didn't mention that, but the whole project was, of course, prefabricated and pre-installed into a factory, such that the whole logistic could be, in a way, also de-risked and simplified the installation on site. So everything here on the left bottom corner are all these main rafters with their steel connection already in place, so they could just be lifted over and bolted together in a quite a short time. And this actually is a picture from this summer, which the project was open ceremony. This is the second project, which in a way is has been the kickoff of everything in ENCODE. It's a project which has been running for about 3 years for us. It's set to open, or actually maybe it is already open to public since a couple of weeks, 2-3 weeks. We have been involved in this project on about 40 different packages over 3 years of time on the interior side of the tower, developing, again, design to production, all a series of stairs, forum stairs, claddings, feature stairs, a lot of elements within the interior, again, part of the tower. In this specific case, I will only touch base on two scopes, which again leveraged Speckle in specific. Of course, the general approach, this is something which is in a way scalable to the other instances as well, but is that we developed kit of parts, which means catalog of elements that could be repeated and reused within the same systems, and eventually, why not, even in other projects as well. So this is, for example, the result of, several months of optimization and iteration of the design parts and systems together with the engineering team, and turned out to be the full final catalog of elements to build like over 30 different stair systems within the atrium of the tower. And of course, kit of parts means also that each element is well controlled, like we know, like, of course, dimensions and all the data are available, let's say, on the digital platform. So these stairs in particular, in this case, was nothing really fancy geometrically speaking, but it had a lot of challenges in terms of systems and prefabrication. So the whole design was oriented towards designing for prefabrication and factory pre-assembly, such that, again, all these elements of these 30 stair bodies could be brought to site and then mounted pretty much like a Lego piece. This was some of the Speckle work using the Power BI connector. Again, this is like about 3 years ago. Very simple dashboards. I'm sure today I will see way more evolved UIs, but it was really helpful to communicate with the fabricator. In this case, we were appointed by the fabrication team, Norm Oil Engineering. And this, again, it was used pretty much like a iterative tool for them to see where all the metadata of the elements, they could query all this information in real time, and we could reissue different versions of the model very quickly through Speckle. This was one of the stair bodies, like a special feature stair on the ground on the lobby, which again we developed completely in Rhino with embedding all these fabrication, installation constraints and data, and then we made available through Speckle, mostly again to collaborate with the fabrication team, which we were lucky to have quite a digital savvy team on the other end, so they could really digest these models and work on their own side. This is another package which relied or used Speckle quite substantially. It looks like a very simple object, but it was definitely not. It's a modular edge boards, which we designed together with the fabricator and the engineering team, which had multiple functions within the tower. It had to coordinate, shape all the concrete slabs of the tower, as well as, in the meantime, coordinating post-tension cables coming out from the slabs and coordinating casting positions of balustrades and stairs. So we developed this kind of template, pretty much, which in ply, in structural ply, that could be positioned on the decking, poured concrete against it, and then removed to fully, let's say, prepare the slabs for installation of the balustrade systems, stairs, and the post-tension cables. And this was an exercise which lasted about over 6 months. There were 27 floors which used this system with very different conditions, different topologies from angles to curved elements, different depths. This was all also happening while the engineering was still getting refined. In this case was Arup working on the structural engineering. So we were consuming data from them and updating this design accordingly through based also some of their parameters. Similar story to the stairs that you've seen before. So dashboards were generated pretty much in real time because we had all the information on the Speckle server, so we could update these dashboards and pretty much make people aware of some of the decisions that were taken during the design development. This is just a little bit of a summary of the process. So we were consuming IFC data, mostly slab edges, and then instantiate our own systems or parametric models onto it, and then going straight from the 3D model to manufacturing. So As you can see, like the balustrades were setting in place, and then the stairs bodies as well. This was one of the modules that was produced. Like, of course, like every time, like in every project, we try also to reduce the number of drawings to the minimum, like potentially even to remove them completely. In this case, for example, we tested different kind of strategies to engrave or embed information directly into the elements themselves, such that would skip the necessity for extra drawings or extra informations. This is just an example, for example, how to self-align plates on these kind of curved elements without the need of any drawings. They could just place them in place and align through these two segment engraved parts, making the whole assembly on site way more intuitive. These were the post-tension cables sticking out. Next project is again a mass timber project, which unfortunately is not going to be built in timber. Last minute got a bit of a kind of redefinition, so it's going to be in steel. But for a long time, like we were very close to get through manufacturing. It was fully developed on completely designed again in mass timber. In this case, we worked together again with Theca Timber and Ergodomus, timber engineering practice in Italy. In this case, like also in the previous project, everything was designed for prefabrication and pre-assembly in factory, and also completely designed for transportation. So considering all the constraints that both the installation team had on site, as well as the logistics of transport from factory to site. We had like quite an intense back and forth with the engineering team in this project, where we were exchanging our graph model with them so they could run their own FE for testing with wind load stresses, and as well as a wind tunnel testing. This is something which, with a bit of time, I would like to get my hands into it and maybe develop the connector for Global, which is quite a common engineering tool in the timber realm, which is currently not in the connectors ecosystem. Again, the whole model was fully uploaded onto the Speckle server. Again, in this case, it was already a bit more of an adoption at the team scale. The first team, we kept using Speckle internally, like in our own on our side, but we steadily, step by step, trying to onboard also the other members of the team, the other consultants, so we could collaborate more efficiently, making things very, visually, also consume visually information in a way easier way, which is, I think, still is one of the crucial aspects in our discipline. And of course, like since we are a completely distributed team, we could start using these 3D commenting features to leave comments to each other. So when Max on the Australian side would pick up the model, had already my feedback on it, they could continue developing the model on his side. Last project, which is this one is about to get built instead. This is like a swimming pool, Olympic-sized swimming pool, feature roof, again in glulam timber, again built in Australia. It's going to be built in Australia. In this project in particular, the complexity, I would say, was definitely less on the geometry side. It's like quite a regular 45-degree grid structure. But the challenge, or at least the fun part, was design it in such a way that could be modularized to let's say, diminish the number of lifting operations that they had to do on site. So the whole system was designed to be built as like a cassette systems like this, like you see on the screen. And then modules, these 23 different modules could pretty much be replicated across the whole roof. So they could be both manufactured again on the factory floor, pre-assembled, brought to site, and pre-assembled on the ground into these kind of cassettes and lifted up directly in position. So everything was, the whole installation process was sped up by a lot by using this kind of methodology. And like summary video, just showing a little bit of how the system works. So we had this kind of long beams coming together and these noggins built together into a cassette system. Again, Rhino work that we do on our side, like we have developed over time lots of different tools and our own C# framework, which allow us to, again, play with data, color things, group things, but most importantly, work, again, with data and geometry. And of course, again, automation played a key role in this project as well, so we could issue both assembly documentation and parts fabrication documentation like very quickly, like in a matter of a week. We could issue over 300 drawings with QA and so on. Also, we have this, we tried recently also to embed or link different representational formats within Rhino itself, so we could make drawings or IFCs or other formats accessible straight from the model. This is the model in Speckle, which this was, I would say, so far the most, the project which adopted Speckle the most, where we managed to onboard again both the supplier and the engineer as well. So we could pretty much did a kind of induction session, like to explain how the viewer works, like what could be done, how could we comment on things, collaborate together. And again, it turned out to be very successful on this end. So all the informations were fully available on the model, and both the manufacturer, which again is going to start in 2 weeks production, could query this data and organize, for example, shipping containers, cluster elements by base, and so on and so forth. This is me and my partner Max, like working together on the same model, like giving comments while reviewing, for example, production drawings and making sure that all the annotations are correct, and doing this kind of QA process live on the model itself. And of course, coordination was played a big role as well. So we could merge. We could merge multiple files from the engineering side, for example, and then cross-check through versioning also that what moved, what was deleted. This was kind of quite an iterative exercise that was very much supported by this versioning, diff versioning kind of tool that Speckle enables. And I think that's about it for today. Thank you very much. If you have any questions.
Thank you, Federico. A moment of silence for the timber that is never going to be used. It's a sad story,
Yeah.
but yeah, we got to see some good viewer action. Got to talk about new connectors coming up, apparently.
Why not?
It's another exclusive from SpeckleCon. What else do you want to ask him about? Here we are.
Thanks for the presentation. Very, very beautiful. And the diagrams were very beautifully put together. Were they instrumental in the design process? And my other question is, who did they communicate to and how? Because they're really beautiful. And I wonder kind of what the scope of that kind of diagramming and explanation was within the project.
Yeah, I mean, I think communication is really one of the most important thing in our field. Maybe sometimes even underestimated a bit, and even visual communication. So producing diagrams or using just the viewer to, again, color code elements, making things very visually evident or consumable, it's, I think, played a really important role in all the projects. Sometimes, at least, we think things are apparent or they are well understood, but they're simply not. So to make good visuals, I think it's part of our role as designers and tech enthusiasts as well, like to make things easy to consume.
Were you showing them with the owner part of that process, or the end user, or was it kind of an intra-fabrication team diagrams? Because they're so clear and really beautiful. I just wonder.
Well, can you repeat, please?
Was the owner looking at the diagrams as well?
The owner.
Or is it more the fabrication team clarity?
The owner, I think, never looked at the diagrams.
It's a shame, they're missing out.
Yeah, maybe one day, but definitely all the others did, yes.
That's super interesting. I have a mass timber background for like 14 years, so it's really on point. I was interested in the construction documentation. So did you use traditional drawings, or was there any sort of 3D usage or adoption there?
Well, I think every project had a bit of its own specifics, but in general, it's quite a hybrid. So it really depends on who is on the other side. Like we could work fully 3D without, passing through all the data which are required, but then it really depends on who is on the other end to consume this information. So sometimes drawings are still the most effective way.
Did you work with like people that were more 3D savvy on site?
Yeah, definitely. Like the tower project, for example, the fabricator, which was also an engineering firm, was quite savvy on the modeling side. So in many cases, we could just issue 3D files without even drawings. So they could just work out of them.
And then that sort of, the model would also represent then the connection intent or the connection design. So they'll just be looking at, there's a bolt there.
Yeah,
I know what the bolt is. I can.
Of course, it was not shown today, but what we usually do is like both 3D work, bringing this kind of level of details into the 3D space, but in parallel develop also 2D drawings, which are mostly working as templates of rule sets. So they kind of embed all the information on a 2D representation, so they could be signed off. Everything is quite easy to track down, approved, and then that scale up to 3D. So it's an hybrid. Sometimes 2D even work better, just faster. Yeah. Sometimes 3D works better. So.
Okay. Thank you. That's interesting.
Sometimes only data, not even drawings. Sometimes, it depends.
Thanks for the presentation. It's really interesting. I love this idea of hyper-realistic models, zero tolerance, I think you call them. Did you have to compromise with the geometry itself before sending it to the Speckle viewer? Obviously, there's a lot of geometry you have to deal with. Did you find any bottlenecks or optimization of the geometry itself?
Well, so sometimes, of course, when the model contains all the bolts and nuts and screws, there are thousands and thousands and thousands of elements. Like it could pile up and become a bit difficult to manage. But it's just about structuring the informations into branches or into streams in a way that you could isolate parts and make it more navigable. So, for example, all the bolting or screws, they are all separated, so you don't want to load them all the time, so you don't really need some time. So it's just to make all things more lightweight. And the same happens on the Rhino side. So when the model is fully compiled, let's say LOD 400, it's really heavy, but it's a chain of models together. So maybe there are 5, 6 models.
Thank you.
Okay, we have some questions there, and I think we're gonna close it up after this one. Who are Specklers? Speak up. There we go.
Couple of questions. When you were comparing the laser scans to the actual geometry, were you converting the laser scans to mesh and then sort of looking at the mesh versus the geometry, or were you just kind of being clever with point clouds and just
Point clouds.
you weren't converting to mesh at all?
Yeah.
So you
yeah.
were just looking for outlaying dots, basically.
Yeah.
Okay. And then when you went to go to manufacture, pretty much, I guess it varies every single time, depending on if you're working in wood, if you're working in steel, as to who you work with. But predominantly, when you go to sort of CNC this stuff out, are you just giving them an STL file, and then they're putting it in what, SolidWorks, or are they putting it in CATIA, or do you know what the output
Yeah. So
MCAD system is?
that really depends again who is on the other side, and that's what I meant to at the beginning of working agnostically. Like by early conversation, we set up this kind of communication frameworks within the team, or in this case with the manufacturer. And sometimes the manufacturer wants directly the CNC file. In this case was a BTL, BTLX format. So we developed the exporter for that. Sometimes they might prefer just to have, like skeletal information, so they have maybe their own pipeline already in place, which works with a certain type of input. So we produce only those inputs. So it's just really like setting up the threshold between us and who is on the other end, saying, look, we need this type of geometry with this data attached, and then we produce them. So it really depends on. Sometimes for everything which is steel, usually is like if it's flat plates or claddings, it's like classic DXF files. If it's milling, there are different type of formats. If it's extrusion, sometimes it's step files. It really depends on the system. We produce files at, let's say, 0 tolerance. So everything is in what is captured in the 3D is what is going to be physically. So if the 3D gets approved, that's what you're going to get. There won't be any, let's say, tolerance issue as far as the system works and it's been engineered correctly. So.
Thank you for the question. I think that, okay. I'm weak.
Thanks for the presentation. Just about a tolerance thing, it's just something that's sort of like, I'm scratching my head about it. So when you scanned it and you overlaid it, did you overlay it with the geometry of the complete structure? Or did you collaborate with structural engineers to rerun a partial analysis of the grid shell partially built, because then you have different deformation in a temporary case?
Yeah.
How does that work, firstly? Secondly, I don't understand the zero tolerance thing. You can model things in 3D with zero tolerance, or how many trailing zeros after the dot in millimeters. But the thing is, like, you're going to weld something, it's going to warp, the heat is going to deform the steel connection. I saw steel plates welded there. So please help me understand what was the point of scanning 3D, point cloud scanning every day. Why wouldn't you use like AR with an iPad and just overlay and say, okay, this is a construction sequence. These are the different temporary conditions and states, and this is how it reflects in the temporary cases.
There are many questions in the same one, so we'll try to summarize. I mean,
Thank you.
So the zero tolerance is meant to be like the digital planning of the elements. So, and to some degree, like some of the deformations or some of the adjustments of the elements are embedded into the design. So everything is designed which is embedded into the elements. It's not just pure modeling, like blind modeling. The systems are designed first to embed future tolerances or system tolerances between elements, for example, which comes from different sources or constraints, right? So installation or engineering and so on. So that's first. And second, the point cloud thing was a necessity in that project because, well, not everything goes always very smooth. So in that case, the whole structure where they started loading the elements on the steel ring beam around started deflecting on the tip, and it deflected a bit too much than expected. So that's why the whole scanning exercise started. So they asked us to again give this kind of analytics built against what was digitally planned. So they were loading one beam, scanning, and seeing how much moved on the tip. So we could, the day after, run this analysis, tell them, look, it moved as much. Maybe we have to integrate packing elements to compensate. And these kind of things happened on a daily basis. So we had to pick it up very fast. But with all these, let's say, procedural methods, and it was quite efficient, so we could do it fast. And on the AR, maybe last. On the AR, I mean, I'm happy to be, to be told I'm wrong, but I think we are not there yet. Yeah. Okay. Fine. Yeah. No. If it's about like really 1 millimeter tolerance, these kind of things, especially on site, at least so far in my experience, was not as reliable, let's say.